Welcome to the Che Institute's Scientific Innovation Series. I'm Chung-Lee Kim, a professor in Department of Physics at Ewha Women's University. Today's theme is space and gravitational waves. And we have Professor Barry Barish from California Institute of Technology, a 2017 Nobel laureate in physics, joining us. Professor Barry Barish is a Lind Professor of Physics Emeritus. He worked on astrophysical particle physics as well as gravitational wave science for a long time. Over decades of his extraordinary research career, he was the principal investigator of the LIGO project and then served as director of the LIGO lab. And also he established the LIGO scientific collaboration for decisive contributions to the LIGO detector and the observations of gravitational waves. He received Nobel Prize in Physics in 2017. And now let me invite Professor Barry Barish to talk us about gravitational waves from discovery to a new science. Please welcome him.
Thank you for the kind introduction. And thank you to the hosts here at the Che Institute for inviting me for this series on scientific innovation. I'm happy to be here and to participate. I'm going to talk today about gravitational waves, and I'm going to take you through the history of how the idea came, and then the technology was developed, and then the science followed. And it's a three-way partnership that I'm going to be talking about. The way our project developed and the way complicated scientific projects, I think, whether they're in chemistry, physics, space, have the attribute that they're a combination of a three-way partnership. In our case, the three-way partnership is theory. Physicists that try to understand the underlying principles and rules and predict things or try to understand things. Experimental physicists who do measurements and develop the experiments themselves and perform them. And the third, which is at least as important, is the instrumentation that goes into advancing science. So we have a three-way partnership, and I'm going to show you a little bit of each as we go along. And in fact, in my first slide, which you see here, you see what just looks like an ordinary laboratory where men are dressed in their white uniforms. What they're looking at is a piece of glass. But it's not an ordinary piece of glass. It's the piece of glass that is a mirror that we use in our instrument on gravitational waves. You see it through it. You see somebody in the back with black goggles on because it's a mirror, but we see through it. The reason is it's a mirror in the infrared, not in the visible, because that's the wavelength that we use for lasers in our experiment. This is the best mirror in the world, anywhere, any optical instrument, anywhere. If you measure the mirror itself, there's a huge amount of technology that goes into something like this. The material itself has to be very pure. In our case, it's fused silicon. It has to be very, very precisely and tremendously precisely made to have the right curvature. And that's what makes what we call super mirrors. And then it has to have a coating that'll reflect the light at the wavelength that you're working at. In our case, it's in the infrared for the lasers that we use. These mirrors took 2 decades for us to develop, and we're still developing mirrors that are this size or even bigger for the future with even better figures of merit. That then carries down to the companies that we help work on this, developing mirrors and other optics that they sell and use technically. So it's not necessarily an invention of something, but by pushing technology very hard to do science, we have a direct influence in basically in how to make, in this case, better optics. So I'll point out a few of these things as we go along. We'll start with a little history. And that's kind of how science develops. In our case, I'm going to talk about two gentlemen that everyone has heard of. One is Sir Isaac Newton, and the second is Albert Einstein. And they are the two people most responsible as theorists for our understanding of gravity. The fact that there's two of them tells you something interesting, which is Newton himself presented his theory of gravity, his life's work, in 1687 in a book called the Principia. And that book, in that book, he called it universal gravity. He figured out not only the formula for gravity, but that the gravity that he was talking about would work whether we're talking about the apple falling out of a tree, or we're talking about the tides, which have gravity, or we're talking about how the moon goes around the Earth, or just two objects like I'm showing here, and how they attract each other. They attract each other by what looks like a rather simple formula. It's the product of the masses of the two objects divided by the square of how far apart they are, and times a constant that actually took 100 years to figure out. Newton didn't figure that out. And that formula works for everything. Newton used the word universal at the end after he had tested it on the planets and so forth, when he managed to predict what the orbit would be of a comet. A comet doesn't go around completely. It comes and goes. And he predicted the trajectory of the most famous comet, Halley's Comet. And at that point, he called it universal gravity. He published it. And you would think that's the end of the story. As physicists, we now have a theory of gravity. But all our theories are really approximations, and it's a lesson we have to learn. It doesn't matter what theory we talk about. It's not the ultimate theory. There was nothing wrong with Newton's theory. It's just not everything you can imagine using gravity. And so despite the word universal, Mr. Einstein came along 200 and some years later and created a refinement on the theory of gravity. And he was motivated by different things than Halley's Comet, for example. And so in Einstein's case, it looks very different. He talked about, we've all heard these words, basically space and time, 3 dimensions of space and 1 dimension of time being unified into one theoretical concept in what he calls space-time, one word. You get a little wavy line on it when you put it into Microsoft Word because they don't really understand that it's one real word. So anyway, that's a new theory of gravity. I put up the formula, but I'm not going to go through it because just to be similar to what's done in Newton's case. Newton's theory of gravity was arguably the most important and successful theory ever in physics. It lasted more than 200 years and described everything, with one small exception by the time Einstein came along. And when Einstein came along, he fixed that one problem, as I'll show. So in 1915, Einstein came along, and without showing you the formulas, what he did was say that the presence of any massive object affects the space around it. So in this case, gravity is not a force, as I say on the right. It affects the space and time around it. Everything, although it sounds like a detail, but it's both space and time together that are put into it, and it all gets distorted. I show a picture here like a trampoline where the object distorted the space that you see, but each point on that is also a time, and it affects the time. So gravity then isn't a force, as I said. It's effect on space and time. Space and time, as it's warped then, tells objects how to travel. And so as we'll see, in this case, the Earth is attracted to the sun because of the warpage, which changed in time, and that's the reason that they pull together. Even though there's the formula that it goes inversely as the square of the distance that was used by Newton. So at the time Einstein came along, he had created and been probably the most dramatic advance in physics in a short amount of time in 1905, when he solved 4 of the most important problems in physics in a matter of months. That included E equals mc squared, relativity, and other features of modern physics. He went on to this problem of gravity, and it took him 10 years. So after doing several problems in months, it took him 10 years to do this problem, because the mathematics of this curvature of space and time and the unification of space and time involved mathematics that even Einstein didn't understand at that point in time. He wasn't motivated, I think, although some biographers think so, by the only problem that existed at the time he came along. The problem is shown here, and that is that Mercury's orbit around the sun is very elliptical, as shown here. Each time it goes around, it's affected by the gravitational pull when it nears the Earth of all the planets, and of course the sun itself. And it doesn't come back to the same point. And as you see on the right, it moves a certain distance. And knowing all the planets and other objects in the solar system, you can calculate how much that movement should be. And the movement, I think I've written here, is a number. In Newton's case, you calculate it to be 532 arc seconds per century. In fact, the observed number is a little bit larger. It's 10% larger. So this isn't a big deviation. So Newton's theory of gravity, which lasted more than 200 years, had only this one small problem in it at the time Einstein came along. This wasn't important, I think, in terms of Einstein developing his theory, but it was important in him demonstrating that he had a theory that was better than the theory that existed before. So in his very first presentations of his theory of general relativity, he used this example as something that it fixed. That's common in theoretical physics. Presumably, if you develop a theory that's better than the other one that existed before, it should solve some problems that the previous one didn't solve. This theory actually solved more than that, as I'll mention. So you probably realized at some point in school or somewhere had the discussion where your teacher said, "What happens when you jump up?" And you said, "The earth pulls you down." But when you said that, which any kid would say, did you ever ask why the earth pulls you down? That's a question that Newton didn't answer. Newton didn't answer why it pulls you down. He just gave us a formula and said it attracts. So that's, again, the idea that any theory is an approximation. Something left out of Newton's theory was why it falls down. Looking at this little picture here, you can understand that when in Einstein's theory, it does tell you why it pulls it down. I show here the Earth, and on the Earth or near the Earth, it distorts the space around it, and you put an object on this, it's going to tend to roll or move toward the Earth. So if you have the distortion of space caused by Einstein's theory, it can cause the attraction that causes or answers the question of why the apple falls. That question was a question that Einstein didn't even talk about in his thick book called the Principia. But the next one he does mention. He realized that his theory did have limitations. And this limitation is the following, that if the apple drops from the tree, in Newton's theory, you know it immediately. And that's okay, the apple's here and we're here. But if you think of the example of the sun, if it were to disappear right now, we wouldn't know it for 8 minutes because that's how long it takes the signal to travel from the sun to us, in this case, at the speed of light. And in Einstein's theory, he says gravity also travels at the speed of light. I'll show you, if I get to it, a demonstration that we know that that's true to 1 part in 10 to the 15 from the measurements that we've done on gravitational waves. So it fixed some problems. But any theory that we take seriously in physics isn't usually maybe even unique if it solves some problems that existed in a previous theory. It usually has to predict something that's new that we can go test. And if it predicts something new, then we can maybe take it seriously. So Einstein, when he presented the theory of general relativity in 1915, showed it solved the problem of mercury. But he also predicted and proposed that an experiment be done and that it would demonstrate that light bends and that he could calculate actually exactly how much it would bend. And so he invented the idea, the concept, to do an experiment where you look at the sun, and if a star goes behind the sun, the light that travels to you as it grazes past the sun will bend. He proposed that should be done experimentally by waiting till there's an eclipse of the sun. At exactly the time there's an eclipse of the sun, watch stars that are behind it and see the bending of light. That idea was then grabbed by Sir Arthur Eddington, who wasn't Sir yet, but became that from doing this. And he made an expedition in 1919 to the southern hemisphere where there was a total eclipse of the sun. And he measured this in 2 different locations. And basically not only saw the bending of light, but that the amount was the same as Einstein had predicted. That's the actual reason that Einstein became worldwide famous. The problems that we physicists grab and make ourselves so much an idol of Einstein, he solved in 1905, but for the public, it was the bending of light. And that became worldwide famous in 1920 when it was after it was seen by Sir Arthur Eddington. So that's Einstein. Another interesting lesson is that we have something like that and we learn. Another thing that happens in physics often is something we discover becomes tomorrow's tool to discover something else. And this bending of light is now a common tool used in astronomy. We call it gravitational lensing, where you can look at an object, like I show in the picture here, where the source is behind the object. We're on the Earth, as shown in the picture. And the light bends as it goes around it, and we can learn about that object, how big it is, and where it's moving, and so forth, by studying an object that isn't necessarily emitting light itself, by looking at gravitational lensing, a tool used in modern astronomy that resulted from a new theory that Einstein had. And these are just a couple examples. The most dramatic one is called the Einstein cross, which is usually visible almost with the naked eye in the southern hemisphere. So we have this now complicated new theory of general relativity, more complicated than the simple formulas that Newton gave. And one might think it isn't useful for anything. However, we all use it almost every day of our lives, and that is the GPS system. So we all know that we have our little iPhone, and we use it to tell where we are, how to walk, where we're going, or how to drive our car. That relies on something like the original one is 24 satellites. The satellites are going about 14,000 kilometers an hour. And when we learn about relativity, we're given a little phrase that tells us what happens, called moving clocks tick more slowly. It's a relativistic effect that actually time changes and how fast it goes. And if we do the little calculation in relativity, we make a correction of 7 microseconds a day. That doesn't sound like very much, but it's actually made in the satellites themselves. So we sit here on Earth, the light goes back and forth, and the correction to the timing is done in the satellites itself. When the GPS system was done, and it was originally done by the military, they didn't believe or understand what general relativity was. So there was actually a lot of discussion before they understood that they had to also make a correction for general relativity. That correction comes because the satellites that are going around the Earth are high up, and they're high enough so that the amount of gravity is only about a quarter what it is here on Earth. And if the gravity is less, then the clocks actually go faster. That's by general relativity. And that's a correction of 45 microseconds per day. So both corrections are made in the satellites. And so the total correction that's made is 38 microseconds per day. I won't go through the mathematics for you, but if I take that and ask if I did not make the correction, how long would you stay on the road before you essentially run into parked cars or something? It's only a couple minutes. So we need that correction to make GPS work. Again, an example of even the most abstract ideas that we have in science, in this case in physics, affecting us in everyday life and being able to do what we do without just the drama of making some new invention. Okay, Einstein predicted something else, and in this same period when the theory of general relativity was being tested, which is all I've talked about so far. In 1916, one year after he proposed that he had a new theory of gravity, he noticed something. He noticed that the equations of general relativity, if he formed them in a particular way, I think I might show you that on a slide, looked a lot like the equations we're used to in electromagnetism. And in electromagnetism, we have waves. So electromagnetic waves, the light waves in this room, radar, microwaves, and so forth. In the same way, if the equations look the same, being Einstein, he didn't prove anything. He made the leap that there must be gravitational waves. So he proposed that in a little paper in 1916. That paper's not very good. It's only a few pages. It has nothing very deep in it. It's just a conjecture, but the conjecture by Einstein. He also made a mistake in that paper. If that mistake had not been corrected, we would have had a lot of trouble understanding the data when we actually saw gravitational waves. He fixed that 2 years later. So 2 years later, he wrote a second paper on gravitational waves in 1918. And that paper was better paper than the first one. He actually showed something that we needed as experimentalists, and that is, how do you make gravitational waves? Electromagnetic waves, I'll remind you, were made by, in a famous experiment by a physicist called Hertz, who took two charges and oscillated them, went in the next room, and saw that he could detect the waves that were made by the two charges, moved his detector forward and backwards, and saw it was wave-like. And that was the proof of electromagnetic waves. I'll show you in a few minutes how we might wish we could do that for gravitational waves. But Einstein showed that it isn't, in this paper, that it isn't a dipole, two charges going like this, but for gravitational waves, it's what we call a quadrupole moment. It's the equivalent of 4 charges moving, and it makes what we call a quadrupole moment, and that's what makes gravitational waves. That's a piece of information we need as experimentalists to know what is going to produce gravitational waves, whether we make it in the lab or some other way. So here's the idea then. We may have to make something that has this equivalent of 4 charges. An example of that is 2 weights going around each other like this. And so I show that in a picture here. If two objects are going around each other, they have mass. The mass is moving or accelerating as they go around each other. They're gravitationally attracted to each other. As they go around each other, then they will radiate gravitational waves. The amount of gravitational waves and so forth we have to calculate, and I'll come to that, but that's what happens. So this is one way to make gravitational waves. You can find other ways that have what we call a quadrupole moment, but this is actually the example of the kind of gravitational waves that we detected in our experiment LIGO. So only one formula. I'm not asking you to really understand the formula, but only for those that do. This is the formula, and I say how on the left. I'm not going to read it, how I generate it in general relativity. But for those who have ever studied electromagnetism, this formula should look familiar. It looks, with different letters, the same as the formula for electromagnetic waves. So this is just a simple way that I basically did what Einstein did in 1915. He didn't really write it down, of how you can take general relativity and make a formula that looks like it's giving waves. So this is the waves that come. But we know then that if we have waves that look like this, they make, from electromagnetism, plane waves, what we call plane waves that travel along. And we know the formula for that. They'll travel at the speed of light, if Einstein's right, just like electromagnetic waves do. Only there's one difference. In electromagnetic waves, there's two components, just like we have in gravitational waves. In this one case, it's E and B. In this case, there's two components. Only if you know a little bit more than I've said, you'd know that gravity has a quantum mechanical aspect, which we call a spin 2, and electromagnetism has spin 1. And because of that, these waves aren't perpendicular to each other, but at 45 degrees to each other. So we expect to see two waves at 45 degrees to each other. And we haven't yet demonstrated that. So in the experiments I'll show, it's one of our goals is to be able to do this. But to do this, it takes experimentally the ability to separate these two waves, which we can't do in LIGO itself. We have to do it with another detector, and the other detectors aren't good enough yet. So we're waiting for a third detector that's good enough to be able to do that. This is a small point, so I'm not going to talk about it today. The idea that there were gravitational waves then just more or less went away. Einstein believed that they would be undetectable. He said that in one of these two early articles. And basically, he wasn't wrong. He just didn't anticipate the advances in technology that were possible a century later. So he didn't really understand that we could make high-powered lasers. There wasn't even a laser at that point, and so forth. So basically, also on the theoretical side, I mentioned he didn't derive the equations of gravitational waves out of the equations of general relativity. Because he didn't derive it, then the problem really wasn't solved as a theoretical problem. He just made a conjecture. And it was controversial for years. He tried again to solve it in the 1930s, and he couldn't develop the equations from scratch either. So it was even after Einstein died that finally the physics community saw proof that convinced other physicists that gravitational waves do come out of the theory of general relativity. That was in a conference in Chapel Hill, North Carolina in 1957, where they had about 50 of the most famous theoretical physicists that worked on general relativity come together to try to see if they could solve what they called the gravitational wave problem, and that is to actually derive gravitational waves directly out of general relativity. At that conference, a theoretical physicist named Pirani, a British theoretical physicist, gave the opening talk, and he did a very beautiful derivation of gravitational waves from theory of general relativity. The second person who was at that meeting was Richard Feynman. And Richard Feynman, in his characteristic way, got up and said, well, okay, so you can prove gravitational waves from the theory, but if it's a real phenomenon, there has to be something that's measurable that comes from it. And he then did a little, what we call a Gedanken experiment to show how you could detect, what an effect would be from gravitational waves. He called it the sticky bead argument when he presented it. And the sticky bead argument I show here on the right is, imagine you have two beads around a rod and then gravitational waves come through. If gravitational waves come through, they distort space and time, and the rod doesn't stay completely cylindrical, but gets distorted with a wavelength of the light. And if that's true, then the little beads on it get pushed back and forth. When they're being pushed back and forth, what's happening is that's being caused by friction, something we learn in freshman physics. But friction is really a transfer of heat, and that's energy. So basically, if we can say that gravitational waves caused a transfer of energy, then it did something real. So that was by Feynman. That idea was picked up to do the first experimental attempts to do gravitational waves, which I'll talk about next. So this man, Joseph Weber, was at that meeting in 1958. And he basically picked up Feynman's idea, and he took a big bar of aluminum. This is one of his early ones. He made bigger ones even. And he put around it very sensitive detectors so that if a gravitational wave went through the bar and it distorted it, these detectors would pick up a little signal. And he made two of these. He called them resonant bars. If the gravitational wave would go through any bar, if you come up to it and you hit it with a hammer, is going to ring at some frequency. So that's the frequency where the bar is the most sensitive, typically around a kilohertz. And the little sensors around it would pick that up. He was at University of Maryland. He put one detector there and a second one at Argonne Lab near Chicago, and looked for them to give signals at the same time. He was a real pioneer in the field, but unfortunately he wasn't a very good scientist because he claimed detections twice, separated by about 10 years, all of which were disproven at levels that were much less sensitive than the actual gravitational waves that we've detected. But he started the field. I was following the field very early, having studied general relativity as a student. And I never liked this idea because somehow you make a bar and it's going to be sensitive at some frequency, which is like a bell that rings at some frequency. But who says the gravitational waves want to be at that frequency? So we needed a detector method, and that's when I became seriously interested, that was able to cover all frequencies, or a large wide band of frequencies, so that gravitational waves could be detected throughout the wide band of frequencies. And that's the scheme that I'll talk about. So I'll talk a little bit about that idea, how to detect gravitational waves. So first thing that you learn as an experimental physicist is, if you're going to be any good, control all the variables. So it doesn't matter whether you're in a little lab or a big lab, you want to control everything. If you don't control things, you make mistakes, you don't understand. And so it's one of the main lessons that you have as an experimental physicist, is to control everything. So of course, in this case, you want to do what was done that Hertz did for electromagnetic waves, which is he made the electromagnetic waves, he went in the next room. So you'd like to do the same thing for gravitational waves. So this is what you might do. You make a big barbell, And I exaggerate. Imagine it has 1,000 kilogram weights on the two ends, and then you spin it. And imagine I spin it at a kilohertz. Of course, you better get out of the lab if you have something like this. And then you detect gravitational waves. If I calculate it doing that, I get in that formula that I showed you at the beginning a very tiny number, h of 10 to the minus 35. This is 15 orders of magnitude smaller than what we've actually been able to detect. So the great romantic idea that you control everything, we had to give up. There's no way at present technologies to control everything and make gravitational waves and detect them. So instead, we had to find a source in nature that was strong enough so that we could detect it after we made a very sensitive detector. And the detection we made isn't 10 to the minus 35, but more like 10 to the minus 21. And I'll show you that's already a very, very tiny number. Gravitational waves then, once I know that they exist and we're relying on nature, we might see things that we don't know about. And of course, that's one of the great hopes in doing this. But there's several kind of sources that we knew could and should give gravitational waves. I list them here. One is compact binary systems. That's the kind of system I showed you, two objects going around each other. And there's several examples of that. There's black holes that go around each other, neutron stars, and so forth. And the second is that we know that in the universe we have stars, they burn up their fuel, and eventually they collapse. When they collapse, they also will give us a burst signal of gravitational waves. So one can look at supernova. A third one is a continuous source instead of just something that happened and it's gone, and that is to look at pulsars in our own galaxy. Pulsars are the product of a supernova. Afterwards, that they're a spinning star that often gives radio signals at a given frequency. And so they give what I call here a periodic signal. And a periodic signal we also can search for. And the last one, which is, I think, to my mind, the reason in the long term why this is going to be a fantastic science is to study signals that come from the early universe. And the reason it'll be so important is there's no other way to go to the really early universe. The studies that we do are with electromagnetic radiation, but the universe was too opaque in the early times to be able to probe directly. But with gravitational waves, or presumably with neutrinos, you could go back to very early times. And I think gravitational waves is the likely way we'll do it, but not this year. So we do the first one, which is this equivalent of the barbell in what we've detected so far. So now let me tell you the effect. So imagine there's a source. It makes gravitational waves. The gravitational waves come to us. We build a laboratory to detect them. So what do we have to detect? We have to detect, first of all, when they're passing through space, let me say they're different than electromagnetic waves. Electromagnetic waves, although I'm going to tell you they go at the same speed, have something that goes with it that we call a photon that carries it. As far as we know, for gravitational waves, at least as Einstein predicts them, are just ripples in space and time itself. So they're more equivalent to going up to a pond and throwing a stone in it. The stone goes down to the bottom, but you have ripples on the top that don't have any carrier or anything that are rippling down the side. Similarly, we have some object that makes gravitational waves, and then we get, going at the speed of light, a distortion in space and time that propagates through space. So they're ripples in space and time. Secondly, the amount of amplitude that I said would be 10 to the minus 35 if we made a little barbell, the big barbell, is in what we measured 10 to the minus 21. So that's my goal. I'm going to show you 10 to the minus 21 what it means in a minute. And what will happen is it'll distort space locally as it passes through, and we can see how much. So imagine it'll change a distance by that little h times whatever the length is. And that I show here. Imagine that you had a ring of free masses, and then a gravitational wave goes through. What's it going to do? It's going to distort it so that it becomes elliptical instead of a circle. And since it's a wave that changes as it goes another half a wavelength, it'll be an ellipse in the other direction. So it'll go back and forth between a vertical ellipse and a horizontal ellipse. So if I can somehow detect a circle changing to an ellipse at a level of 10 to the minus 21, the number that I want, then that would mean if I had a 1 meter circle, I'd have to be able to see the difference to one part in 10 to the minus 21. That's a very small number. We make a detector where the circle is a kilometer instead of a meter. That's the reason it's so big, to make this number more palatable. And so ours is 4 kilometers long. And that means that 10 to the minus 21 becomes 10 to the minus 18, which is 1/1000th the size of a proton. So we have to see an effect that's much smaller than what we study on particle accelerators. The technique that we use is, again, an experimental technique that is one of many, but an experimental technique, the experimental limitation is the following, that if I try to measure something absolutely, it's really difficult. So if we want to know what a kilogram weighs or how long a meter stick is or whatever you want to measure, we have big institutions that study that. In the US, it's the Institute of Standards that measures it. There's a big institution in Paris that measures and keeps track of what a kilogram is. If instead we try to measure the difference between two things that are supposed to be identical, we can do that much, much more accurately. We don't need these big institutions. The best technique that I know of to do that is what we call interferometry, which is what I'll talk about. And the idea is shown here and shown in the next couple slides. And that is, we generate light with a laser. We send it along and put it through a mirror that divides it, sends half of it in one direction and half of it in the perpendicular direction. If we make the two arms that it goes down equal length and put a mirror on the end, the light then comes back at exactly the same time. You can reverse one from the other, they'll cancel, and there's no signal in the final thing. So I'll show that in a little movie in a second. So this is the light going back and forth. They cancel. My detector's down here on the right. And as I move back and forth, I create a signal. Or I'll show it with real light, which is in waves. It propagates down to the mirrors, bounces back, and then if the two come back at the same time, they cancel each other, which you're seeing here, and the detector sees nothing. But if they come back at slightly different times, which I'm going to show now, then they'll add together and the signal will show in the detector. So this is the most sensitive instrument that I know about to measure a difference. So it's the instrument that we used. We gained some sensitivity by making the arms very long. And so that's the scheme that we used. However, we're trying to do it much, much better than anyone has ever done interferometry before. We built two large devices in order to do this. This was developed we started doing this work in the 1980s. We were approved to actually start building it in 1994. We finally detected gravitational waves in 2015. So it's a long saga to do that. We have two detectors. They're separated by 3,000 kilometers. That means that if I have a signal that's coming in from the bottom, where it says Livingston Observatory, at the speed of light, it would take 10 milliseconds to cross the US 3,000 kilometers and get to the other observatory. Or if I started at the top and go down, it would come 10 milliseconds before. So that means that the two, no matter where the signal comes from, they're going to be within plus or minus 10 milliseconds of each other, and we then require a coincidence to that accuracy. So here's our two detectors. They look very different in these pictures because one's in high desert in Hanford, Washington, and one is in a commercial pine forest in Livingston, Louisiana. And although the sites are very, very different, the instruments we keep on a daily basis identical. So if we change an electronic circuit in one, we immediately propagate it to the other so that they're kept as exactly identical instruments at all times. And that is reflected when I show you the data. You can see they're the same. So the idea again was shown here. Now I'll show you what limits this. That's a scheme. What limits you in doing this scheme? First thing is that I make these long arms. There's the problem of the fact that there's molecules between the mirror at the beam splitter and the mirror at the end in 4 kilometers. In fact, there's so many molecules that we have to use vacuum. Not only that, in order to keep it small enough, we have to have what's called a high vacuum. A high vacuum is a very, very good vacuum. And this system that we have is the largest high vacuum system in the world in the 2 interferometers. There's a bigger vacuum system at CERN, but not all of it is high vacuum. In the high vacuum part, we're the biggest in the world. And so residual gas is the first limitation. Second one is the laser. We all think of a laser as being fantastic. It points in a wonderful direction. But actually, it's not good enough for us. We have to stabilize it in its wavelength, in its amplitude, and its pointing direction much better than that. It requires a lot of sophistication to do that. A third limitation is the test masses themselves. Basically, whenever we have anything at room temperature made of atoms, even in a solid, they move around. And so we call that thermal noise. Ideally, you'd like to take these test masses and take them to very low temperature. And we'll probably do that in a decade or so, but it's a very hard problem to have the right materials and how to do it. So presently, we work at room temperature. I'm sorry. The one I talked about above, my label says seismic noise. So room temperature is what I just showed. Also, we have seismic noise, meaning that the mirror itself, and I'm going to come back to this, is shaking because the Earth shakes. And so that limits us, and we have to keep it from shaking. And that's the practical problem that I'm going to point out is as one we had to solve to do this. Lastly, we have very sophisticated effects. We have what we call quantum noise, and actually are publishing papers on quantum effects in large objects that are being published in physical review letters. But for us, it's a problem. And that is, as we increase the amount of light from the laser, it puts pressure on the mirrors. And so they want to move the mirrors just by the pressure from the number of photons hitting the mirrors. So the radiation pressure has to be compensated against the fact that you want a lot of photons. And that's what we call quantum noise. And we do a lot of tricks to try to solve that problem, something called squeezed light. So we end up with a detector that has this characteristic. What I show on the bottom is the frequencies that we detect. You'll notice that the frequencies go from about 10 hertz to 10,000 hertz. That's the same frequencies that our ears work at, communicating with each other. That's no accident. We're trying to do an experiment here on Earth, and it turns out that evolution has worked for us in picking the place where the Earth is the quietest. And so our ears work from about 10 hertz to a few thousand hertz. If you went to lower frequencies, the Earth shakes too much. In fact, if you look at the line on here that says seismic, it's falling very, very, very rapidly. In terms of a power, it falls as frequency to the 4th power. So what I show here is what limits the experiment. The shaded region is where we can detect. And below that, we're limited by all these experimental problems. And when you see the real data, it will look like this. This is the real data. This is a history, just to show you again how experimental physics works. When we first turned on the interferometer, it's the very top ones. And we'd learn from it, fix things, make improvements, make inventions, until we did better and better. This is about a 5-year history, going down to a line that you can see on the bottom, which was the design line of where if we weren't limited by some practical effects, we could get to. And that's the scheme. We actually looked for gravitational waves for more than a decade during each of those times. Didn't see any. Then we made a major improvement to the detector, and that was to actually improve enough so that we should be in the region where we thought we could detect gravitational waves. And that required 5 years of turning it off and making a whole new detector itself. And the improvements were first to make the ability to have a high power laser. That involves not just having a high power laser, but taking care of if you have more photons, stray light, scattering in the vacuum, and so forth and so on. In the middle frequency range, we needed better mirrors, what we call test masses or mirrors and suspensions. And we designed a whole new one. I'll talk about it for a minute. And at the very lowest frequencies, we needed to have better what we call seismic isolation. Seismic isolation is preventing the shaking of the Earth, which we don't feel very much, but our instrument does. The other point is if you improve the sensitivity a factor of 2, what we measure is what we call an amplitude, not a power. And it means that we can see a factor of 2 further out in the universe. But if we see a factor of 2 further out in the universe, the volume change is a factor of 2 cubed. So it's a factor of 8. So improvements very rapidly improve our ability to see gravitational waves. At low frequencies, we actually improved almost a factor of 100. And if I had to pick one thing, that's what enabled gravitational wave detection. So the big problem for us, if we just take the biggest problems physically, were 2. One is to do interferometry at a level that's orders of magnitude better than anyone had ever done before. And in fact, if I tried to characterize it, you can look on the lower right, we had to do it where we could tell a change in length in the 2 arms to 1 part in 10 to the 12th. Some of you might have someday seen an interferometer in a physics lab and saw fringes, and maybe were able to tell the fringes to 1 part in 10 or 1 part in 100. A very good interferometer that people use commercially might be 1 part in 1,000. We had to do 1 part in 10 to the 12th, which meant there's a whole several decades of inventions and innovations that went into the interferometry itself. The last thing was to show you a more practical problem. The biggest one was the vibrations of the Earth. And again, we had to be able to isolate this. We live here on the Earth. We have the machine on the Earth, but we don't want to detect anything from the Earth. So it has to float effectively above the Earth, again, to 1 part in 10 to the 12th. So that's a very practical problem. The interferometry I won't talk about because it's very sophisticated. I'm kind of showing it in steps here to get to the kind of level where we could do 1 part in 10 to the 12th of the wavelength of the light. The other one is a more practical problem, and again, I think illustrates where I started this talk, which is the interplay between technical things that we develop in experiments. Maybe the interferometry that I just mentioned is developed for ourselves and isn't needed at that accuracy for anything else, but this is. So we had to isolate ourselves from the Earth better than anyone ever had, a factor of 10 to the 12th. We did that with no new inventions, but with some sophistication and developments. So the idea was the following, that we know how to take care of bumps in frequency. We do it all the time in your car. It has a shock absorber system. And the shock absorbers basically take the fact that when you go over a bump, it's at high frequency and you don't like it, it doesn't feel well, and it can't get rid of the energy, it's there. But instead, the shock absorber system takes and moves it to lower frequency where it just feels smooth to you as you go over a bump. So we just took the same idea, basically shock absorbers, only we made the world's best shock absorbers. They're little springs with just the right cushiness. And we made 4 layers of it. Your car has 1. And so if there's still movement after the first one, you have a second one, third one, and a fourth one. And with that, which is I think the fanciest shock absorber system you can even imagine, we got 1 part in 10 to the 10, which is pretty good, but not good enough because we wanted 1 part in 10 to the 12. So again, we basically grabbed something that people had already developed, or at least the idea, and employed it. That is, most of you have seen one time or another these little earphones that you put on in an airplane that magically make the sound of the engine go away, and the stewardess comes up and asks you if you want coffee or tea, and you can hear her perfectly well. And that's done by sensing the ambient noise from the engines and canceling that, but noise that isn't ambient but is real spikes you can hear, so you hear the stewardess. So we don't have anything to do with noise, but the idea is the same. So what we do is put inside of this seismometers all over, which measure the residual shaking of the Earth and the direction, which is harder than the earphones on a plane, and we push back and correct for it. And that gave us the last factor that got us to 10 to the 12th. And if I picked one technical feature that enabled gravitational wave detection, that was it. So rather mundane. All the other improvements were just not worth going through now. So let's look at the detection just for a couple minutes, and then I'll end this lecture. So the idea is that we're going to take 2 objects that are going around each other gravitationally, and they're losing some energy to gravitational waves, so they'll in-spiral very slowly. If we take 2 objects, it may take millions of years for them to do that, but there's ones that have been doing it for a long time somewhere in the universe. So that's the idea. While they're just in-spiraling, which is what I show in this hand plot on the left, they'll follow a curve where it gets a little higher frequency, higher amplitude as they're moving toward each other. And that you can calculate very precisely using Einstein's theory of general relativity, and we do that. Then when they actually come together and merge, it then is a new area of physics that Einstein can't calculate called strong gravity. And it's where we expect, if there's a different theory than Einstein's, where it would be applicable. So that's strong gravity. And then finally, when this comes together, it'll ring a little bit, and we call that a ring down at the very end. And that, again, we can calculate. So I've kind of shown that by the middle being completely unknown. How do we look? We then look using what's called match filtering. So we don't have any way to find event candidates electronically as we're running, like you do in particle physics. Here we have a stream of data, time frequency data, and we basically calculate the possible orientations of 2 objects that might be in the sky. It might be one that's the mass of our sun, another one that's 10 times the mass, or it might be 2 that are 20, and we calculate the whole possibilities. Something like 300,000 to populate basically the region where we would have the frequencies that we're able to detect. And that's shown in the 3 colors here. The 3 colors basically are the region which would be the biggest one is where you'd have 2 black holes. The region in the lower corner is neutron stars, and the red region is neutron star and black holes. And so we do 300,000 calculations in advance. We have all of these to compare with the data, and we compare it with every piece of data as it's going along using a technique which we call match filtering. So that technique I'll show here on the right. So you see it happening. We're just multiplying a known waveform against the data. And if it ever finds that, you're then able to see a signal where it's at. And this is the capability that electronic engineers have developed to find signals or see signals that are much smaller than the actual ambient noise. So we're able to see signals that you can't see basically with your eye that are buried in the noise. And that's the technique that we use on every piece of data as it's going by. And this is just a picture of an actual event where the high lines are basically the noise, and there was an event which I've basically drawn in it smaller than that gave this signal so we could look at it. So that's a technique. Finally, after 30 years of developing this, we had improved the detector, and this is the first event. What to notice, this is the event that was in newspapers around the world and so forth. What's shown is a plot where going left to right, it's 0.2 of 1 second. So we're watching the time evolution over 0.2 of 1 second. Going vertically is this sensitivity that I mentioned, and you'll see, if you can see it, that the sensitivity shown here is 10 to the minus 21, the number that I showed you, which is the biggest signals that we see. And so in 0.2 of a second, you see in the top plot the data from the state of Washington, Hanford, and the middle one, our detector in Livingston, Louisiana. And to the eye, except for the color being different, they look pretty much alike. And if you put them on top of each other and compensate for when the small time difference, you can see that they're on top of each other, and that's the first event. This is the same thing, but I just want to show the third panel. The top is our data, which has noise, so it shakes around a little bit. The middle panel on the top is the calculations of Einstein. And the next panel, which is the one as an experimentalist that I looked at and was immediately felt that this was real, was subtracting one from the other. And in that way, if there's something that's still there, that's noise or problems, you see some shape, but you'll see it's just noise going back and forth. So that was kind of the proof to us that we had something. There's an enormous amount of information in that waveform once we get it. And you can use that to calculate the parameters. And so we do that, we calculate the parameters, and the first event, which I think I have here, is here. So that was 2 black holes, one 36 times heavier than our sun, 36 times the mass of our sun. A second one that was 29 times the mass of our sun. We know that adds up to 65. And the final one, which we could measure, which is 62. So the difference between those is 3 solar masses, 3 times the mass of our sun. So what that tells you is the equivalent of 3 times the mass of our sun went away in the form of energy, in the form of gravitational waves, in 0.2 of a second at the time this energy was released that we detected. In some absolute sense, that was the brightest thing in the sky at that moment. So anyway, we measure the parameters, the masses, the spins, and all of that. I don't have time to go through that. We also can look at how well it matches all of this and whether there might be something which would be the equivalent of the photon, which we call a graviton, which does not exist in Einstein's theory. And we don't see any evidence for that, so we set a limit for what it could be, which is by far the best limit around. I just want to show one other thing, and then we'll end. We test general relativity. We've made hundreds of detections by now. We're trying to see where they come from by measuring the parameters. what's the mass distribution, where are they, how far out are they, and so forth, to try to understand the origin, which we don't know. They could be primordial. They could be somehow made from heavy stars. We don't yet know. There's different theories. I'm going to skip that just from time. This is kind of interesting events that we've had. I want to show one more thing, and then I'll quit. Finally, in 2017, another detector became available, not as sensitive as ours, but enough to help so that we could tell where something came from in the sky. With two detectors, we can only see a ring in the sky. With a third one, we can point and see where it is in the sky. What I show on the plot on the right is just LIGO itself with previous events where we could just see a strip and not really tell. But once we added a third detector, even though it was less sensitive than ours, we could tell where something was in the sky, and that immediately paid off. We basically saw this signal here. What's shown in the top is satellites, two different satellites, that we're looking at high energy photons. And so they mostly just see noise, but you can see a signal off to the, see if I can use this thing. It's the top one maybe. Oh, right here. And the line that comes up, that's shown up, is from the plot on the very bottom, which is LIGO and its time frequency data. And you can see the signal from LIGO was within 2 seconds there when the signal was seen of these high energy photons from the same place in the sky. That told us that we saw something that was important enough to alert the whole astronomical community that there was a signal that they could see. Black holes they can't see. This is neutron stars they could see. The difference in time between these is interesting because we now know that this event was created by a merger of two neutron stars at about 150 million light years from the Earth. We were able to identify, with the help of the electromagnetic detectors, the galaxy where it came from. So 150 million light years away is 1.5 10 to the 15 seconds it took for the signal to get here. And the difference between our signal and this one is within 2 seconds. So it tells you immediately that the speed of light and the speed of gravitational waves are the same to within 1 part in 10 to the 15. You expect the signal from the neutron stars, the electromagnetic signal, to come afterwards because we're detecting the merger and they're detecting the nuclear physics that emits photons after they've actually merged. So that's not to be taken seriously, but the fact that it's the same to 1 part in 10 to the 15 is an impressive verification of Einstein's theory. I'm going to skip that. It's just how we localize, which I'm not going to do. I think I just want to show one more thing. The future. So we've made a lot of improvements, and this is just to give you an idea of where this is going before I close. Each time we basically, like on most experiments in any laboratory, whether it's a big lab or another, you take data for a period of time and then you stop, make improvements and take data again. In our case, as I pointed out, making improvements, we quickly improve the event rates. So what I show here is the very first run, which is the one on the left, the second run, the third run, and the run we just started 2 weeks ago. And you can see the fast slope change. So we're now at a stage where we're seeing, although the discovery was only a little more than 5 years ago, we now see an event of some sort every couple days. And you can even track it on your iPhone. We have an app that you can watch if you'd like. I'll tell you where it is. And that's the science being done in that. And I think our plan through this decade, we have basically funding and a whole plan for how we'll upgrade through the end of this decade. And the hope would be to make a new generation of detectors in the 2030s that'll be even more sensitive. This is only part of the problem. You can do very different frequencies like we do in electromagnetic waves. We have infrared, ultraviolet, X-rays, and so forth. And it's a combination of all that that's made such progress in electromagnetic radiation. And here, likewise, you can go to different frequencies. So what we have planned is 3 satellites in space. It's called LISA, and it's an approved project funded by the European Space Agency, mostly a little bit of NASA, and it's scheduled to be launched in the early 2030s. And that'll cover, I'll show you where, that'll cover where it says LISA here. This is a frequency band. And then lastly, at very, very low frequencies, there's an experiment which just announced what they think is the detection of gravitational waves at even lower frequency by using known pulsars and the fact that they're all over the place. And if you watch the timing of them and a gravitational wave comes through, it changes that timing somewhat. And they just announced what they feel is an observation in the last week or 2 weeks. So this is a picture of what they do. And that's their signal, which I won't take time to go through. And thank you.
Okay, thank you very much for your very informative and interesting talk, Professor Barish. Actually, I still remember to get searching for presentation materials for myself when I was a PhD student, and then naturally I discovered your slides. I still saw some of you used some of the materials from the old times, and very nice to see those. And I would like to thank personally for providing us, everybody in the gravitational wave science, these amazing educational and presentation materials.
Thank you.
Okay, so there are many questions we would like to ask, not just the science, but also about the leadership, about to form international collaboration doing mega science in this 21st century. So the first question is goes like this: the tireless efforts to build a detector to discover gravitational waves began as early as 1950-ish, as you said. Theoretical backgrounds and all this experimental effort, commissioning effort, took more than 30 years of time. This research journey must have presented numerous challenges and moments of anxiety, actually, to scientists and everybody involved in this big project. What serves as your driving force to continue this research throughout the decades?
Oh, the driving force. The ultimate goal, of course, is the driving force. But as an experimental physicist, you're constantly solving problems.
Mm-hmm.
And I enjoy that from the time I was a kid, solving problems, doing puzzles, whatever. So yeah, the eventual final one is making detections. But from the beginning, whether you're conceiving of something and then you realize you're wrong, or you build some electronics and it doesn't do what you want or whatever, those are all the kinds of things that I think it depends on your personality. You could be frustrated by. I think this is the extreme. My stuff is the extreme example of needing to not have the psychological attribute that people call a need for instant gratification. Mm-hmm. I don't really have that. So if you need, playing video games is instant gratification, or doing something that you finish by the end of the day, or this or that. I don't really, my personality is a little different. I'm not driven by that. So basically solving the infinite number of problems from when we started on this in 1980 or so till we made detections is basically a lot of fun. I feel privileged to do it. So.
Right, thank you.
And there was never any problem that was so serious that I didn't think we could solve it. So maybe if we ran into something and then you realized you you couldn't solve it, that would be different. But we just had problems that were fun to solve.
Right. So many questions from maybe like young children as well as parents or adults from the public is when you started this big science with very fancy goals, did you really realize what would be your outcome? Did you have vision? Or you just do everyday small steps one by one throughout the 30 years of time and then coincidentally found something? So,
No, we had a goal.
oh, from the beginning.
From the beginning, yeah. I mean, I think from the beginning we thought that using modern technology and the scheme, as I said, I followed this from the first experimental attempts, which I didn't like, while using these bars. But once just the idea of using interferometry came, I thought it was well matched to what we had to do. And although the problems were incredibly difficult to get that kind of sensitivity, there was nothing that you could identify that would be, even though we didn't know how to do it, that would be a killer or something along the way. So I never lost confidence that we could do it. It's just it took longer than maybe I'd like, and but as I said, most of it was fun doing it along the way. So.
So as a side question, during your talk you mentioned Joseph Weber's work was really innovative, but maybe his failure is attributed to this narrow band capability of the detector.
Yeah.
So how did you start this project? Did you already knew laser interferometry could do this broadband search and then pursuing the technology, or did you know the requirement from theoretical background and search for what can realize this broadband detector? Which way was the case?
Yeah, it was a combination. I knew of the problem. I took general relativity as a student in graduate school, and in fact, I was better at general relativity than quantum field theory, which is the theory behind particle physics, which I did most of my life. So in some sense, I felt a little, even though it's so difficult, better with this theory. It's not really as abstract as quantum field theory. It's just difficult. So I knew of the theory, I knew of the prediction, and I knew of Weber's work. I thought Weber was really a very creative and talented experimentalist and a poor scientist. He made two declarations that he detected gravitational waves, which were wrong and hurt the field. And so somehow his, drive to be famous and make a discovery, I think, overcame the creativity which he had. I didn't like the technique, but the idea of that, as far as he developed it, I thought was good. Once interferometry, and I didn't invent it at the beginning, the idea of interferometry was first, the very first people that mentioned it were two Russians in a journal which most of us didn't read in the 1960s. And then in the 1970s, there was some, not studies exactly, but suggestions of doing it that weren't the Russian ones we hadn't read. And then there started to be some R&D being done. I was doing particle physics, so I was just interested intellectually. Then at Caltech we have one theorist, Kip Thorne, and once interferometry was starting to be a possibility, he and I talked about forming an experimental group at Caltech. But I was busy with particle physics, so but I was a big supporter of starting it. So we started a group. I didn't think I would work in that group because I was working in particle physics. But it turns out that because I helped start the group and I stayed very close to it and I'm at Caltech. I was deeply involved in the Super Collider, but when it was canceled, my colleagues went to Geneva, and instead I did this. So,
Right. So speaking of the SSC, Superconducting Super Collider, I read your lecture, Nobel lecture actually, and you did mention that you were the director, and unfortunately the project was cancelled by the U.S. Congress. So comparing between two mega projects, the particle accelerators versus LIGO project, uh, maybe it is very important to gain the public support, not to mention the well-defined science goals and everything. So as the principal investigator and the director leading this whole project and make things successful at the end, could you explain the strategies you employed for LIGO comparing to your previous sort of failure experiment, experience?
yeah, I mean, the Super Collider was bigger, so it's a bigger problem and had more politics in it than this. I think when we were funded for this, we had the support of the director of the National Science Foundation. At that time, it was Neil Lane, who later became the president's science advisor. And the National Science Foundation is in the U.S. I think is like anything, it has its flaws, but it's a ideal organization for somebody like myself who really is motivated by science itself. Because if you go to NASA, these are all good organizations, but you go to NASA, you can go to the website and you'll see a mission statement, which is there, or the DOE, and the mission statement in high energy physics is written down. The National Science Foundation's mission statement is pretty simple. It's one word, science.
Oh.
And to me, that symbolizes the fact that that's the big romantic goal and what's behind anything done, that's not small scale, say, at the National Science Foundation. So when we got our funding for LIGO, it was important to get it in a way that it was supported by the director of the NSF. The DOE is somewhat larger, so it's not possible to do it quite the same way. So I'm not comparing in that way, but I think it helped us a lot that during our tenure, we must have had 4 or 5 different directors, but we always kept the NSF as partners, not reviewers, if you want. I mean, they have to review you and so forth, but they were always they treated us and we treated them as partners in an adventure. And to me, that helped a lot with going to Congress, the public. There was an openness and sharing. And the last thing is that as a leader of it, I was always extremely careful not to overpromise. And we often overpromise because we're very ambitious, but that's the quick way to lose the confidence of the public. And we made no promises that were that we didn't reach. We shared our problems. We had problems because we were not well liked or believed in by the astronomers.
Yeah.
And astronomers are different than physicists in that they're observers, so they get an instrument, they observe. And the idea of having to solve a whole years-long technical problems to do something. And our science is somewhere in between the kind of science that you do in physics and astronomy, where we call our runs observing runs,
right.
Well, instead of experimental runs, and so there's even though we're completely funded and supported by physics, there's an overlap with astronomy, and that community is a tough one for us because of their approach being a little different.
Right. Right. Recently, I also realized that the astronomy community slowly embrace the gravitational wave community.
Oh yeah,
More
now they love us.
F-
But
Yeah, neutron stars.
yeah.
Yeah. So at the beginning of your talk, you mentioned the interplay between three partners: theorists, experimentalists, and also instrumentation. So how do you perceive this interplay in advancing science? Could you elaborate a bit more? And could you also, how can I say, explain why R&D, decadal period of R&D is really crucial to reach this big science?
Yeah. First, let me say it's changed a lot. When I was a student and went into physics, I was working on particle accelerators. There was nothing that we used that industry had. I mean, it was basically developed. Of course, in the end, some of the developments, whether the use of accelerators for medicine or using the techniques that we use in building and using accelerators or particle detectors was useful, but it basically all was one direction. It was developed by experimentalists, usually in big, what is now called Department of Energy laboratories, and some in universities. And so once I became not a student, but a scientist that picked your problems, one of the main ingredients in trying to not be a failure or be able to pick something that you're going to succeed at was the technology, the problem of having the technology, even if you thought it could be done, but actually it wasn't in hand, the technology you needed to do the experimental work that you do. That's changed. So if I look at my students now, I think that they are better off than I was, that there's now a whole outside world of advanced technical tools that haven't been yet applied fully to physics problems. So when I was a student, I had to figure out whether I was able to do what I wanted to do as an experimentalist, could build it or solve problems. And now I think a clever experimentalist needs to understand everything that's going on, whether it's advanced electronics, computing, AI, machine learning, whatever it is, where it's not being applied, and that they can solve problems that haven't been previously solved because there's tools that haven't been applied yet in physics. So I think we're in a great time now for, let's say, young experimentalists to be able to there's real opportunity where we haven't yet used all the tools that are being developed outside. That said, a lot of things that we develop have a big impact on society. And in two ways. One is that I give an example of having to protect ourselves from the shaking of the earth more than anyone's ever done. Mm-hmm. It turns out that technology is very likely to have a fairly large impact. It's expensive. Clearly, we made it so we didn't make it to make zillions of them. But it turns out, for example, microelectronics. Microelectronics, if you ask what limits that right now, it's the stability of the tables. And so we've worked with a small company on part of the problem of solving this, because they're not interested in us, but they're interested in the idea of being able to make more stable tables and so the same with the lasers. So the laser technology that we've developed even in the early times has been applied to making accurate printing and things that people use lasers for. So being able to stabilize the lasers, which is one thing that we've done. So often, even though you don't have a goal, but it's an interplay now of us applying what's out there
Yeah.
and us developing things that
Yeah.
can be used. So I think the connection between technology and industry is much closer than it's ever been. And to do experimental physics, as I said, I think it's a three-way partnership. It's technology, experimental techniques, and theoretical.
Right. Thank you very much. As a quick question, do you remember how many patents have been published through this LIGO project, or how many companies has any relation for any profitable business out of this LIGO science?
Yeah. First, often there's two things. One is, did the science that you discovered, was it applied? First, it's too soon. But secondly, it's a very small effect, so I can't imagine what gravitational waves will be useful for. But I'll give two examples from my own career that what we like to call curiosity-driven research has had unexpected and large consequences. So when I was a student, I was in Berkeley, and in the Berkeley labs, they were studying in optics labs. They were studying again, a little bit like me, they were studying a particular effect that had been predicted by Einstein called stimulated emission.
All right.
This he predicted in 1919 or something like that. And that was being done several places in the world, but it was being done in Berkeley at that time. And that was observed, and they proved a principle of Einstein's called stimulated emission. It was done completely in what we like to call curiosity-driven research. No other reason. Nobody had any idea. They won the Nobel Prize, by the way.
Yeah.
Nobody had any idea of what it might be used for. And it was at least a decade before people realized that having this stimulation which was focused was useful, and it's the laser, one of the biggest industries that we have. So the laser didn't come about because of a stepwise development of technology, but a scientific discovery of stimulated emission, a principle of Einstein, and then applying it to something. A second example, both were close to me. I was working at Cornell on the synchrotron, and again, it was somebody else doing something else. But at that time, there was again another theoretical proposal that people were trying to observe called nuclear magnetic resonance. And it was observed several places in the world, but one was at Cornell, so I was aware of that. And again, it was a fundamental discovery, and somebody won the Nobel Prize for it. And it was a decade later or sometime later, that people realized that this had the potential of being the best imaging device for medicine that we have. We don't call it NMR because we don't like the word radiation. So it got renamed as MRI.
That's the reason.
And that's what an MRI is, yeah. So it's the best imaging. And both of those were close to me. Both of them came from absolutely fundamental curiosity-driven research. So the research that we do doesn't always do that, but there's enough examples where people have done absolutely fundamental research and even fundamental research that is accidental discoveries. The discovery of penicillin was an example of a serendipitous discovery, where he found mold growing he went away on vacation and found mold growing on his Petri dishes. I was curious about the fact that it was getting eaten away by, and he took a side trip, which is we do with curiosity, and discovered basically what's penicillin, which has increased our lifespan probably 10 years or so of antibiotics. So that's fundamental. It comes out, and certainly all you can say is that learning new knowledge is going to pay off sometimes. I gave the example of general relativity, enabling us to do GPS, for example. So that's just the science itself. The second is the technologies that we develop that get used outside. And the example I gave from Mars that hasn't happened yet is making stable tables, for example. There's a lot of examples of using radiation for different things that particle accelerators do. In U.S., specifically in LIGO, we haven't a lot of inventions. What we did was a lot of refining, I'd say. We didn't invent the shock absorber, we just made it better. We didn't invent, these earphones that you put on. We just used it, stole it, and made it better. So we've refined things, and that's helped companies more than, and helped industry in some ways where we push things more than in patentable. It just happens we didn't go in a direction where we didn't invent interferometry. We just made things a little better so we could do our experiment.
It's amazing that how like a small efforts to make things better can reach the precision to explore the whole universe. Yes. So maybe you didn't have time during your lecture, but could you make some more comments about what is the significance in the gravitational wave detection? And also, could you...
In the what detection?
What is the scientific significance of the detection of gravitational waves? And also, at the end of your lecture, you touched on this gravitational wave background discovered in the nanohertz. That's completely different frequency band. Could you describe what synergy you expect, or what is your prospects onto the future of the gravitational wave astronomy?
Okay, so I'll talk a little bit romantically. Astronomy started in 1610 or whenever, when Galileo took the fact that people had developed lenses that were pretty good for eyeglasses and made a telescope. He didn't invent the telescope. And he looked at Jupiter and saw that there were 4 bright objects, and he thought they were stars. But he watched it for a period of time, and they didn't move like stars. So he discovered the 4 moons of Jupiter.
Yeah.
Now we know there's 100 or something like that.
Yeah.
But he discovered the 4 moons of Jupiter. That was the beginning of modern astronomy. It was the first time that astronomy was done using an instrument other than the naked eye. So, and astronomy has gone, 400 years. It's gone a long ways since then. But one of the big, if we come more recently, I would say the biggest, in my scientific lifespan, the biggest change in astronomy that's made such a big difference is that they started doing astronomy not just in the visible, better and better and better, like Galileo had done, but started to look at electromagnetic radiation from astronomical objects in the infrared, the ultraviolet, microwave, and so forth. And that's been incredible, because you can look at the same object and look at it in the different wavelengths and really understand the science of that object, the origin, and so forth and so on. So multi-wavelength astronomy has been a big gain. If we project, and for saying, okay, we have a historical precedent with astronomy, what should happen in gravitational waves, and give us 400 years, it's going to take a while. The first obvious one is to do the equivalent of multi-wavelength gravitational waves, that we happen to pick a frequency band that we could do here on Earth. When you go into space, you do a completely different frequency band, lower frequencies. I mentioned at the very end that people have been using the timing of pulsars to go to even yet lower frequency. So doing what astronomers have done, the same objects at different frequencies, will give us a better picture, and that's obvious. But there's a feature, I think, of gravitational waves that's, to me, the ultimate goal. And the ultimate goal, in my mind, is to do not astronomy with gravitational waves, but to do cosmology with gravitational waves. And I think we don't know how to do this yet, so it's going to take a while. But if we look at what we've learned about the early universe, the best tool of recent times has been the study of the cosmic microwave background. And looking at the details of it has been surprising, but very revealing. We have big puzzles at earlier times, like something we call inflation. We don't know what happened in the first instance, and so forth. But the trouble is with these electromagnetic cosmic microwave background experiments, they basically can't go any earlier than about 400,000 years after the Big Bang. And that's because the universe was opaque to electromagnetic radiation before that. So they're being very clever now in trying to see, for example, the imprint of gravitational waves, which have been earlier, on the shapes that they get, some polarization effects. That's still very limited. You're actually taking photographs, in a sense, 400,000 years after what you want to learn and trying to understand it, and it's very hard. If you want to go back earlier in time, you can't use electromagnetic waves. So there's two possibilities. One is to use neutrinos. But the trouble with neutrinos, the technical trouble with neutrinos, is neutrinos that were made in the very early universe have been around for so long that they've what we call thermalized. So they're very, very low energy. And the problem is that neutrinos interact proportional to their energy. So when they get very, very low energy, they don't interact very much. And so it's hard to conceive how to, unless you use the whole Earth or something, it's hard to conceive how you can make a detector for neutrinos, even though the principle of going early you could go back to a first few seconds in time. So the ultimate probe of the early universe, we don't know how to do it, is gravitational waves because they're not absorbed. So you could go all the way back to the very earliest times. And to me, that's the ultimate goal.
Yeah, exciting. Just like what we can see different colors by electromagnetic wave spectrum, we can see in the future the different masses, the dynamics of stars and galaxies using gravitational waves. Right. So also in your lecture, you showed us the rapid increase in the sensitivity of advanced LIGO from the first observing run, and now we started the fourth observing run since May this year. After the pandemic, very long waiting. So could you briefly mention what is the main science goal about this current ongoing science run, observing run, comparing to the previous runs?
Yeah. So I would say two things. One is, of course, we hope to see something new. But that, who knows? We might. We haven't yet seen signals from spinning pulsars, which give electromagnetic signals, radio signals. Right. That depends on how spherically symmetrical a pulsar is. We haven't yet seen signals from a supernova. So those would be new. In terms of the science, and maybe not, and as we get more sensitive, a better chance, but I don't know. But so I'd say that on every run that we do. But in terms of what we've already done, I would say that we have, like happens in science in general, we have puzzles already that may be real or may not be, but we need to understand them. The first is that with the very first observation, we already as often happens in astronomy, showed that what astronomers thought was wrong. That is that the belief is that the black holes that we were looking for come from the death, a supernova death of a heavy star. But stars are believed to only be able to be so heavy, maybe 20 times the mass of our own sun. And if they're heavier than that, then they're unstable because they get hit by radiation and they fall apart. So they're not supposed to be stable if they're heavier than that, according to astronomers. The very first measurement that we made, the black holes were 30 and 35.
Right. They were too heavy than expected.
Yeah. So so that created an immediate puzzle, which we haven't solved yet. That is, where did these black holes come from? The astronomers like to stick with their belief, and they may be right, and we just have to understand how, and that is that there are heavier stellar black holes than we thought, and maybe that means that there's more stability against radiation, or parts of the sky where there's less radiation or something. But that's one possibility. The second possibility is that these have come by making smaller ones the way astronomers would have thought, and that through time they've grabbed other ones and merged and merged and merged and built up to bigger ones. That would be a dynamical mechanism. And the third possibility, which to me is the most intriguing, is that they're actually primordial. Yeah. And if they're primordial, then we're learning something about the early universe. And so how do we tell? We do what is tried and true in physics and science, and that is learn more about what we've been observing. So in this case, what we want to do is observe where are they coming from. And now by saying that we get more rate in the new one, it means we're looking further out. So what is the distribution of these as far as distance? And is there any indication that there's more further out or closer and so forth? Then there's other parameters that we can measure that can give us some clue about whether these things like dynamical mechanisms might have played a role, like measuring the spins. As we get not just better rate, but better sensitivity, the events that we have better signal to noise, and we get more information on those things. Thirdly, we have, which is almost inevitable in a kind of crude beginning in a subject, is we have puzzling events. So, for example, we have a couple events that get up well over 100 solar masses. There's not supposed to be black holes between these ones at lower masses and the one at the center of our galaxy. And so they're called intermediate mass black holes. People have conjectured about them. We've seen at least one or maybe two examples. To me, even more interesting, but maybe measurement problems, I don't know, is that we measure after a merger the parameters of them, and we have they're starting from the mass of our sun. The smallest mass objects are neutron stars, and they're well known, measured, and they're 1.4 times the mass of our sun with some error. And then the next heavier object is black holes, but to be a black hole, you have to have enough gravity so nothing, including light, can escape. So people believe that the lowest mass you can have and be a black hole is, I don't know, four solar masses.
3.
Yeah. And we see events in between.
A
couple in between. And so maybe we think we know our measurement errors, but maybe it has something to do with measurement errors. You need more data to be able to tell. And so we need to find more. I mentioned that we have now an app. You can watch it.
Oh, the gravity wave, the detection
Gravity
app.
wave. Yeah, so you can watch it, and you'll see that we have several examples that are at least candidates. And that we just started running 3 weeks ago, 2 weeks ago, and there's several that you can go from that to look at the data that might be in between. So I think the most intriguing thing right now in the data we've seen is whether there's sources whether there's objects in between a neutron star and a black hole.
Right. Right. You just mentioned about this app that can be shared by anybody, literally, not just scientists
Yeah.
and the public
Yeah, but
or
you just go
worldwide.
onto your thing and
Right.
download it for free,
Exactly. So,
and you can watch it, and you can see the events come in. And
right.
and if you click on the right thing, you can go actually look at the more detailed data.
Right. So these days, big science naturally called for international collaboration, and LIGO scientific collaboration consists of like more than 2,000 scientists and engineers.
Yeah.
How and establishing this a healthy working professional work environment is very, very important and got more attention. So speaking about this well-being of scientists individual level as well as the collaboration, could you comment about how first, how did you maintain your like a personally healthy lifestyle to be good scientist? And could you also comment how one can form like a professional but yes still friendly international collaboration?
Yeah, there's no magic formulas to any of these things. Personally, I take care of myself, and I enjoy life. If you enjoy life and you take care of yourself, and you're lucky, you kind of live a long life and you can stay active. So I don't have any magic there. As long as I'm healthy, I stay active. I enjoy doing what I do, so
Yeah.
why not? In terms of collaborations, I've worked in many collaborations in my life, and they come about in different ways. In our case, I would say it started in a healthy way because it didn't start because of politics. It didn't start because of pressure from somebody. It started because of need. So when we started doing this at Caltech, there was a second group that started developing interferometry, maybe even a little before we did it at Caltech, at MIT. And at some point, the NSF, you start developing the technology, it gets more and more expensive. Not the kind of expense is the real thing, but these were just laboratory things. And at some point, the NSF said they didn't want to support two different R&D. They were R&D at that time at Caltech and MIT. And so basically we had what you might call a forced marriage. NSF saying, we'll either choose one of you or work together.
Yeah.
And they told us to work together. And so we did that. That turned out to be a great collaboration, but it didn't happen out of the way you'd love to be. Like your colleagues decide to work together. It was forced by the NSF. At some point, when we got to the stage where it became a real project and we had problems, I'll pick an example. We didn't have the skills to do all the things at the level that we needed, or even to conceive of them if we couldn't do them immediately. So a simple example is the laser. Okay, the kind of laser that we have to have is very special. It's a single line. A laser, we pick a frequency, but we work in the infrared that just says you have the laser, but the laser has to be stabilized in everything. It's power, and you want a lot of power, and you have to stabilize the frequency much better than people do, and the pointing and so forth. And this was a forefront laser. It's the one that people needed for printing and so forth. And so what we did, and that's why I say it grew organically, is I realized that we needed more expertise. And so what I learned was there was a group at Stanford that was developing these lasers and were considered one of the best groups. And there was a group in Germany and a group in Australia, 3 different groups. So I went to all 3 groups and said, how would you like to work on LIGO? Everybody was romanced by the fact that they might participate in gravitational wave discovery. And in this case, they were also very intrigued that the people that published in the same areas they did, but they didn't work together, that they would work together. So we brought in those 3 different laser groups. Then, of course, they brought in some of their friends, colleagues in their own university that maybe knew a little bit more about general relativity or something else we're doing. So they became real groups. But the group started by laser expertise. And I wouldn't say all groups that joined were quite as clear as that, but that was pretty much the idea that our collaboration is a little different than particle physics. And particle physics, which I worked in most of my life, in some sense, a collaborating institution is supposed to bring a dowry. You know, you contribute something to the detector. You might have to get the money from DOE or something, but you contribute. In our case, it was more, we never looked for that because the money we had from NSF. So we weren't looking for that kind of contributions. We were looking for people that would bring something we didn't have. At some point, it was some data analysis, noise techniques, data analysis techniques. And in each case, when we identified some area where we could strengthen ourselves, we tried to identify the right people and invite them. And some people came to us. So it just kind of grew organically, but I think in a very healthy way. So the collaboration still is thriving, and I think it's a healthy collaboration.
Yeah.
We also separated it. We did another thing that was maybe sounds bureaucratic, but was important. And that is that the real money to build LIGO and so forth is in not the LIGO scientific collaboration, but what we call the LIGO laboratory. The scientific collaboration doesn't get the NSF money, but to build the detector comes to Caltech and MIT.
Yeah.
And so we call that the LIGO lab. We have a couple other institutions, Florida and Stanford, because they worked out that are part of it, but and in a limited way. But the people in the LIGO lab that want to participate in the experimental part and not have to join the collaboration. So the collaboration was meant to have no favoritism, that people from Caltech and MIT had the most influence or power. And generally the spokesperson has been somebody from some place. Yeah. Also, the development of the tools for data analysis were new, and so it was challenging. And now we're trying to find creative ways of using machine learning, and again that brings data analysis kind of people into it.
Yeah. So it seems like maybe particle physics community would be more organized from the beginning, but actually, as a member of LSE, I appreciate this loose, organic structure to be creative, to be more collaborated with ad-hoc questions. That I think mostly fruitful for young career researchers in particular. I think we have to ask this question. So, as the highest honor for the researcher, maybe winning the Nobel Prize holds immense significance. So what qualities and actions do you believe are essential for conducting groundbreaking research? And could you give any advice for early career researchers aspiring to make significant contributions?
Well, you have to have a certain amount of luck. So that's luck. But as a scientist, I think the two driving factors that matter the most? Well, three. One is a personal quality. I think the main feature, unique feature, not unique, attribute that is important for scientists to be a really good scientist, I think, is to be driven by curiosity. And curiosity is something that all kids have at a young age. So if you go around young kids, 5-year-olds, 7-year-olds, they're all asking questions all the time, and they're pests, actually. And we don't do a good job with young kids. We basically don't. Our schools are too structured. Our parents tell them to stop making such a mess. And I consider myself to be kind of lucky that I escaped from the fact that people beat out the curiosity in you. And the feature that I think is common to the best scientists that I know is that they're driven by curiosity. That's not true of the general adult population. So it's a unique feature in that scientists, I think, is a quality that we have that's unique and wonderful. The second is maybe more practical, and that is that scientists should be good problem solvers and like to solve problems. So the two features that you need to do, other than a little bit of talent, but is to like to solve problems and to be driven by curiosity. Those are the two things that I think are common in the best scientists that I know. The third one is more psychological, if you want. That is, if you take my work, which is pretty extreme, taking decades to get to a goal, is that, and it's even more true of younger people now, is that if you're driven by the need for what I would call instant gratification, don't be a scientist. That's what you use the internet for and all this kind of stuff. If you need to be do something where you solve a puzzle or do something an hour later, it's not it. I think that the fact of having some patience and not having the cycle, that's not necessarily bad to need instant gratification, but I think it's not a good personality to have if you want to do science. It leads to too much frustration. So when you talk about students who get frustrated and this and that, I think a lot of it has to do with a lack of kind of just enjoying solving the problems and taking your time and not instant gratification.
Right. And as for like teachers and parents, could you give some insights or guidance to foster the development of future scientific minds? What we adults should do for younger generations?
Well, the first one I'll repeat, and that is curiosity. You should realize that that's a great attribute in kids, and we should not just. It's true that schools are the worst. They beat it out of you. They don't let kids display their curiosity, but it's also true of parents. And I think that not just to do science, but I think to be kind of imaginative and creative in life, it's a wonderful attribute that kids have when they're young. Why do a few that manage to somehow hold on to that, and I'm one of them, go on in life? We should be much better at stimulating that and through life. The second isn't just advice for parents, but maybe for young people who want to go into science. And I think, and that is, I think it, to me, other than curiosity and so forth, the most important driving feature for myself is that it's always been a lot of fun. And I think that if you start and want to be in science and you're frustrated all the time, then maybe it's the wrong game because it's a lot of fun. Solving problems is fun. Doing this is fun. It's a privilege and it's fun. And so you should have fun.
Right. Okay. Maybe. Okay. So maybe last question. Uh, so going back to the question about international collaborations, the collaborative efforts underscore the international nature of the project, given the current backdrop or heightened geopolitical tensions and challenges increasing technical decoupling. How do you envision the future of big international science?
Yeah, it's a problem that we've had for a long time. If we go back to the Cold War, that there was probably the best communication between the West and the East with scientists. I went to the Soviet Union twice during that period. Scientists, I mean, we use the term, but I think it's true, and that is science has no borders. Politicians and countries have borders, but it doesn't. If we talk about gravitational waves here in Korea or at Caltech or in Russia, for heaven's sakes, it's the same. Science is universal, and we don't have borders. So borders are made by politicians, which tells you something else, which is that maybe we have some of the secrets of how to get along, and the differences in selfishness or whatever countries tend to develop that keep from having not just countries can have different personalities, different priorities and stuff, but when it starts to become competitive and difficult, then we have problems. And it's been true through history. I think somehow scientists have bridged that better than most of society. And so maybe I mean, we have a term, science diplomacy, which I've been kind of active in, but I think the diplomats and people could learn some things about how we collaborate, and that people are the same, and that we even have the same desires on very deep and frustrating levels, like trying to solve big science problems. And there's no difference. There's no difference between the laser physicists that I talked about in Germany or at Stanford or in Australia. They work together, and this gave them an opportunity to work together in our collaboration. Not that our collaboration is the right thing, but that scientists would benefit more by more bridges together. We don't need to kind of isolate ourselves, and we want to open ourselves also to different cultures. There's the big movement for open access to all our journals, and something that is not. It sounds great. Everybody should have access to everything, but like other things, there's practical questions. In this case, it's finances. How do you make the journals and pay for them if nobody has to pay, or if the paying isn't it? But you want it to be available to everybody, and so some of these problems are hard. But I think as scientists, we're trying to solve them. And open access, I think, is a good example. We try to put things on the web, but we can't do it fully because of the fact that there's practicalities having to do with financing journals and so forth. And we can't completely go to using it on the web because people want to still use publications as evidence that somebody's done something.
Yeah.
Give them tenure or whatever. So it's complicated.
Yeah.
But I think scientists are better at, we have enough commonality that we've learned how to appreciate each other, appreciate differences, and to work together. And I hope that some politicians will learn that too. It disappoints me that in my country, we have one PhD, happens to be a physicist in all of Congress. So our government is made out of lawyers and businessmen, dominantly. That's in a practical sense. It means that they make decisions about things that are technical that they're probably not qualified to do. But I think in a more important thing, they lose some of the perspective that the scientific community has about life and getting along and so forth that we're pretty good at.
Yeah. We are done, but can I ask one more question? Okay, thank you. So speaking about the communication between science community and all the other areas, including public and politics, uh, what should we do to improve our communication, and how we can improve the science, the public education, so to speak? I don't want to say we educate public, but what roles that scientists should do more to promote science in public?
We do much better than we used to do. I think I think two things. One is that the bad thing that we do that we need to correct and learn is not to talk down to people. That as scientists we treat them like they don't really understand what we do. So all of us don't understand general relativity. But when I talk about general relativity, I try not to make them feel they're talked down to. And for example, so in some sense, in sharing what we do, even in casual conversation, there shouldn't be talking down somehow. That only alienates people. The other is, of course, to find every way we can to share the excitement and the questions and the science that we do. And I think we do much better than we used to, but we can do better, a lot better than we do now. And I think probably the most important is to do what I said with very young people. Somehow we have to solve the problem of letting them have their curiosity, but also to expose them to the kind of way we think and do things scientifically. It's important even if they don't end up being scientists. There's just, what I heard today, fact-based decision-making, for example. It's obvious to us, but it's not somehow obvious. It's a term now that's used, but it's not obvious to the public. And the fact that we have fake news and things illustrates the fact that we don't have, we haven't raised the public to a level that they can question what they're told and be able to tell that it matters what the source is. And so somehow teaching the public and kids to think maybe a little more analytically, or however you want to say it, that scientists do, I think everybody would gain. And that's it. I don't know.
Right. I was surprised by this genuine excitement from the public when the first the public release of the GW15114, the first detection of the gravitational waves actually made many people happy based on curiosity. So I feel obliged to sharing this experience rather than lecturing things as you mentioned. Indeed. Yeah. Okay. Thank you very much. This concludes today's session of the Choi Scientific Innovation Series. Let me thank Professor Barish for this information and very inspiring talks and discussions. And thank you all to our viewers on YouTube as well. Thank you. 감사합니다.